Okay. So we can use voltage divider this direction. We could also use it the other way using our resistances. So, or using our reactance. So the reactance of capacitor 1 over the reactance total. So either way, so like I said, that's why I was wanting you to go through your thought, because yes, you are correct. You can do it based on your capacitors or the reactance values. So which direction do you want to go through it, Spencer? Okay, that's fine. So we can do that. So you take the voltage of capacitor 1 is equal to your voltage total, which is 9 volts. Multiply it by the capacitance total, which was 4.25 nano, divided by the 8.5 nano. .5. Because the nanos will cancel. Okay, so where we have this guy, so now we have 4.5 volts being dropped across capacitor 1. Okay, Max, what's the voltage of capacitor 2? Mm-hmm. It's going to be the exact same. Because remember, this is capacitance total. This is the capacitance of the parallel branch. Because you add them together. Yeah, because you got to remember, those combine together for one value, because voltage divider only works with series objects, series components. You get 4.5. Yep, you could also use Kirchhoff's law. Mm-hmm. Yeah, because everything else has to be dropped across that, because that's the only thing left in the circuit. So you have 4.5 being dropped across C1. You have to have the rest being dropped across that those parallel branches, and those parallel branches are going to have the same voltages. You could. Because he hasn't been picked along. Okay, Spencer, current total. Yep. Reactance total was 29.959. Yep. What angle? at 90, positive 90. Okay. Okay. So coming back, so our XC total, we have the total capacitance of 4.25 nanofarads. Okay. So when we plug that into our formula, we get the 29.959. So we have 1 over 2 pi times 1.25 meg for our frequency, and then the 4.25 nano, which is our total capacitance. Do you have a problem with getting the 4.25 nanofarads for total capacitance? Okay. So we'll take a step back. So we have to solve for the total capacitance. With these guys in parallel, how do we add those values, or how do we take care of those values? We add them in straight because they're capacitance. Capacitance we treat as the opposite of when we do with resistance for those. So because these guys are in parallel, we add them directly. So we have 4.25 and 4 1/4. That gives us 8.5 nanofarads. Drops it back down to 4.25. And so then we have this value. So the other thing we can do is let's double check that. Okay. So our XCT is going to be equal to XC1 plus XC2 in parallel with XC3. Right? If we're looking at it from a resistance standpoint, we'd have this formula. So our X of C1, we plug in this value, 2 pi times 1.25 meg times 8.5 nano, we get 14.979. Okay? So then we look at XC2 and XC3 because they're going to both be the same. They have the same frequency, same capacitance. So we plug 2 pi, our frequency, the 4.25 nano, and we get the 29.959. So if we take this, we take the 25.959 in parallel with itself. We can either do that product over the sum, we can do the inverse method, we could take that value and divide it by 2. Either way, we're going to get so this one just happens to work out where everything adds back up to the same values. Make sense? Okay. Solve for the current totals. Now we need to solve for the current C1, IC2, and IC3. The next winner gets to pick which one they want to do. Okay, Jessica? Huh? You want to do IC1, IC2, or IC3? IC2 is not. Okay, come back and look at our schematic. Okay, what's IC1? Okay, so what voltage? 4.5 volts. And the reactance is? Okay, so what's the current? Okay. Also, looking back at our schematic, what current's flowing through C1? The total. So IC1 is also the same as our total current. Did you have a question, Morgan? No. Okay. No. Seth. Knife edge. Okay. You want to solve for IC2 or IC3? Okay. Okay. I will award you 3/4 points. What you should have told me was, I want to solve for both. It was a trick question, yes. Those are going to be the same.
Well, yeah, they're all the same.
I know. Like I said, that's why I'll give you 3/4 points for that one. Because the correct answer you should have said was, I want to solve for both. 75% Okay. Because the two branches are the same, they're going to have the same current. And the other way we could do this is, what current does C2 and C3 have to add up to be? 300, our I total. And if they are the same, they're going to drop the exact same, which means you take this value and cut it in half. Because we have two branches. If we had 3 branches, you'd split it up in thirds. If they were all the same. All right, last ones we have. We've got power total, power capacitor 1, power capacitor 2, and power capacitor 3. Again, winner gets choice. Which one would you like to solve for? Okay, power capacitor 1. .352 watts. Okay. Okay, Morgan, which one do you want to solve for? C2?
Oh, yeah, I guess.
Yeah, C1's already been solved.
Whatever. Okay, so C2, you do the 9 volts or the 4.5?
You do the voltage of that capacitor.
It's current, right?
Yep, voltage times current.
So you do times 1. Equals 675 volt 923.
Okay. You'd like to solve the puzzle? Okay. The other way we could also found this as well is because, again, we have the same voltage. We've got twice as much current. Here we have the same voltage and half as much current. So this value, So C3 and C2 are going to be half of C1. Okay. And our last question is power total. The names are getting fewer and farther between. Oh, back to back. $1.352?
Maybe I wrote it down.
That's the power for capacitor 1.
Where I did. Never mind.
This would be 4.5 volts times the 300 milliamps.
It's 2.7.
It's fun how these problems sometimes work out. Okay. Even though, like I said, we did have an easy problem. Okay, the numbers matched up really, really nicely. Okay, they're not always going to be that way. You're still going to go through the exact same process that we were doing. That's why I wanted you guys to start, giving me the individual voltages, individual currents, things like that. Okay, we treat these guys just like as if they were resistors. Okay, we're not doing anything different to it other than doing an alternating voltage and changing frequency and introducing frequency into our equations. That's the biggest difference that we have with these guys. Okay, would you guys like to do another example of a series parallel capacitor one? We got one no.
No,
Hard
hard pass.
pass. Okay.
Let's put the other option. Yeah, can I hear option 2 before I make my decision?
Let's see, option 2.
And we failed the quiz.
Yes, we did fail the quiz. Voltage by frequency? I don't believe so. It could be, but
That's just how often it happens.
yeah. Honestly, I don't think it is anything.
Well, name it after yourself, and I'll do something.
Okay. So basically our options at this point, do you guys have any other questions about capacitive circuits and AC? They are, like I said, they work the exact same way as resistors. The only difference is we have to find the resistance, essentially, the reactance of a capacitor at frequencies. Okay? So here's some other questions. If we had the same circuit, and we were coming back here, what's going to happen to the reactance values if we increase the frequency farther? It's going to go down because we're increasing the denominator, making that value larger, which means the overall value is going to get smaller. We're dividing by a larger number. Okay? What if we increase the capacitance? What's going to happen to the reactance? It's also going to get smaller. Okay? The only way that the reactance values get larger is if we increase or decrease our frequency or decrease the amount of capacitance that we have. Okay? That's going to get really important to recognize that relationship. Okay? What's going to happen to these components as frequencies pass through it? Okay? Yeah. So door number 1 is we do another one. Door number 2 is, if you guys don't have any questions, we dismiss early. Door number 3 is we start in RC circuits.
We can start RC tomorrow.
Yeah.
RC might be appealing. I think we should do what Ryan did. Down the road, turn it down. Oh no, I'm talking about the noise that he made. Which one?
Yeah, which one?